So mu is the average price of a 3-year-old SUV. The car dealer claims that the average price of a 3-year-old SUV in good condition is $20,000. So the claim is for mu. So how would you translate the car dealer's claim in terms of a mathematical expression using mu?
U equals 20,000.
Mu equals 20,000. So that is the claim. So I'm going to write the claim to be mu equals 20,000. In the problem, it is given that alpha is 0.25. It is also given in the problem that the average price that you found out using 22 vehicles is 20,640. The standard deviation that you determined is 1990. So you think the car dealer is ripping you off, or you don't trust it, then, but we'll see what statistics tell us. The first thing to do always is to write the null and the alternative hypothesis. So H naught, H1, or HA. If you mess this step up, everything that you do would be meaningless. So be careful when you write this. What is, or let me rephrase that. Where should I put the claim statement? Should it go in the null or the alternative? The null, and why is Emmy, why is it the null? Because there is an equal sign. Once we sort this part out, well, the alternative is simply the opposite of the null. Mu is not equal to 20,000. In our problem, the claim is the null hypothesis. I'm just going to write it right there. As I mentioned last time, it is strange in practice for us to use the claim to be the null statement, but is it wrong if we did it that way? Not really. It's one of my pet peeves to do this. That's why I'm complaining. Alpha is 0.25. It is the maximum probability of a type 1 error under our assumption that the null is true. X bar is given, S is given, M is given. So what should we find?
Yes.
We had a formula for this last time, which is X bar minus mu naught divided by S over square root of N. We know the value of X bar, we know the value of X, we know the value of N. Do we know mu naught?
Yes.
What is mu naught?
20,000.
Mu naught is 20,000. It is the value that you see in the claim. So the average 20,640 minus 20,000 divided by 1990 over square root of 22. And what do we get?
You get
1.508.
yes.
$1.508. Now to obtain a conclusion. what type of test are we performing? Are we performing a right-tailed test, or a left-tailed test, or a two-tailed? Two-tailed. Why so, Sam?
It's an average, it has to be within a certain range of values. That's my assumption.
Okay.
But also, it's not pointing any direction.
What was it? Was it you or you? Well, why did you say two-tailed?
It's an equal sign.
Because one, it's not pointing in either direction, it's not equal to sign. And that is the usual approach. Two, as Sam mentioned, we are looking at the range of values right in the middle, to two-tailed test. By all means, a confidence interval and a two-tailed test are statistically equivalent. So, where should the rejection region be? Should it be on the left? Should it be on the right?
So,
Both. So when we did the graphical analysis last time, they simply used that as the real number line. I like to do it separately, but it's entirely up to you. So that's a real number line. So we want to find a critical value which corresponds to the area that we have under the curve. What is that area and that area?
1.50.
1.50.
Oh, wait.
It is an area under the density curve.
Oh,
It is a
okay.
probability.
So 0.025 and then another 0.025.
Why 0.025? It's 0.05.
Yeah, you gotta do alpha for two both sides.
So since it is a two-tailed test, we have to divide alpha by 2. So the total amount of error that you need to, maximum probability in making a type 1 error is 0.05, and we're doing a two-tailed test, so you can go wrong that side or this side, so we divide it by 2. To find that critical value, what did we use in the calculator? Inverse t. So t sub alpha over 2, comma n minus 1. Do we have to find those?
No.
You find one, multiply by -1, you get the other. So t sub 0.025, n is 22. 22 minus 1, 21. What do we get?
Negative 2.07.
Neg-
2.08.
Okay. If this is negative 2.08, that value is positive 2.08. So my decision boundary is 2.08 on the right hand side, negative 2.08 on the left hand side. If I exceed 2.08 or go below negative 2.08, I will reject and annul. So where does the data put me? The test statistic came from the data, so that's what the data is telling us. So where does this test statistic go on the real number line? Here, there, there, there.
Around there.
That was an easy question. So 1.508. Did the test statistic fall in the rejection region? The rejection regions are here. the test statistic is outside the rejection region. So the test conclusion cannot make sense. From a statistical standpoint, the conclusion of the test is not to reject a null. So we have the statement in the null, which is mu equals 20,000. Alternative, mu not equal to 20,000. And that is my claim. The conclusion is to not reject null. In other words, we do not find support toward the alternative. We are keeping the null. So I kept the null, which means the data gave me evidence toward the null. So did we find evidence toward the claim? Yes. So did the car dealer, did they try to rip this person off?
No.
No. The car dealer was actually right. Now, the point of a statistical test is sort of revealed in this problem, should be. If you just looked at the average, is that number equal to 20,000?
No.
No. But did I conclude that the car dealer was lying to me? No. Even though this number did not match what the car dealer claimed, I still found validity toward his claim. Why?
Because it was not rejection.
One, that's what the test told us, but from a practical standpoint.
It's not that far away from the mean.
One, it's not that far away from the mean, that is correct. And why should we bother about that little detail?
Because it's less than that standard deviation way.
Okay. Anything else?
It's not an extremely odd. It's not like extremely.
Again,
It's not in the
It's the word being odd. It's not extremely odd in the sense it is not. We want to give the benefit of the doubt because the sample that we collected is rounded, right? What we are saying is, if you didn't believe the car dealer, even after this test, you can go get another sample, and the chances are it's going to also like it. Does that make sense? So if you want to raise time, go ahead and raise time. Do we follow? Okay, so after some struggle, we used the sample, we found the mean to be 92,068.88, and the standard deviation to be 12,671.61. We can't use the same test statistic. First, we've got to recognize the claim. The claim in the problem is that the average salary of a senior level product manager is, or engineer, is $98,000. In other words, equal to. So what type of test are we going to perform? 210.
Oh, yeah.
So mu is 98,000. The sample that you collect is less than 98,000. By all means, you should get the job. I mean, if they offer, you should take the money, right?
Of course. Oh, yeah.
98,000, they're actually giving you more money. So on average, it's just 92,068. So we want to know if the claim is true, even though the sample mean does not match the claim. So where should that statement go? That statement has to go there. The complement of that would be the alternative. Now we just have to plug in the mean, which is 92,068.88 minus what is mu naught? 98,000 divided by standard deviation over square root of 16. And what do we get?
1.872.
1.8.
Negative.
Negative 1.872. Makes sense. Should we or could we use the same critical value as the last problem because alpha did not change?
Yes.
Nick says yes. Sam says no.
Wait,
What would I say?
wait, the alpha is 0.05.
N's different.
Alpha is 0.05.
Okay.
I
Why
thought you were
no?
saying N's different.
N is different. It's not the same sample size. The critical value depends on alpha.
Oh, I
and
thought you meant alpha.
Oh.
I thought you said alpha. That's yeah. So no.
Can't say no after we gave the answer. 16 minus 1 is 50. So what is the critical value?
It's
2.13.
2.13.
Negative 2.13 on this side, which means 2.13 on that side. So that is our test statistic. The test statistic falls right here. Should we reject the null? No. So the conclusion would be to not reject null. If we do not reject null, is the claim, in other words, did we find evidence to work the claim? Yes. So whatever we claim ends up being true. This is what we call the critical value method to find or obtain a conclusion. The other method is the p-value approach. And we talked about this not last class, but the class before. You're ready? So p-value is simply the probability of a type 1 error under current evidence and the assumption. But there is a method to find the p-value. In this case, the p-value, since it is a two-tailed test, it is twice the area above the absolute value of the test statistic. Good. So there are two ways to do this. You can find the area above there, below there, add them together, or simply look at the absolute value of the test statistic multiplied by 2. So absolute value of negative 1.872, positive 1.872. I should probably use a different color. I want to find the area above the absolute value of 1.872. Let's see if you remember the stuff. How do we find H?
You take 2.13 minus 1.872.
Oh,
Oh,
Normal CDF.
Nick says normal CDF, Sam.
I was gonna say.
So how did we find the area under the curve? Area under the curve corresponds to cumulative probability. So in the past, we used normal CDF. But if you look at the test statistic is T. The critical value is T.
I was gonna say, track one, CDF, is greater than CDF usually goes less than.
Okay, that's correct. So what I'm going to do is instead of using normal CDF, we have to use TCDF. Pick up your calculator, go to the usual spot where we have normal CDF. If you scroll down, you should see TCDF. So instead of normal CDF, we're going to use TCDF. The process is exactly the same.
Yes.
So where does the area start? It starts at 1.872. Where does it end? E99. One difference between TCDF and normal CDF is that with normal CDF, we entered mean and standard deviation. Here, you have to enter the degrees of freedom. If you have the fancier calculator or the fancy calculator, you would see a field that says DF. You just simply put in 15. Once you get the probability, which is what?
0.04.
0.204.
04.
0.04.
We'll multiply by 2 is gonna be 0.08.
I'm to that. 0.04, more less.
0404.
Oh, okay. So common mistake is to not multiply this probability. So multiply that by 2, get 0.0808. Good. So the p-value is 0.0808. We got the conclusion already. So if you look at the p-value, the p-value is 0.0808. Is that bigger than the alpha value that I set at the very beginning? Yes. So that is the maximum probability of type 1 error that I was willing to tolerate under the assumptions that I have. I use the data. The data gives me that the probability of error is going to be 8%. So that's what I can tolerate. Data is telling me 8%. Should I reject or not? I should. That makes sense. Don't make sense. So that and that process are very related, but the interpretation is different. In this case, the p-value is bigger than alpha, so we reject the norm.
I'm sorry, I'm so confused because from my understanding.
Sorry, don't reject the norm. Go ahead.
From my understanding of what you said, you enter for the lower value 1.872, right? And then the upper E99, and then the DF is 15.
It's not 0.0404, is it?
No, it is.
Is it?
I got negative point.
Oh, it can't be negative. No.
Okay. Do you know what I would have done?
So we'll look at it. And
Okay.
so 0.872, E99, 15. Expected it to be a bit bigger. Oh well. So p-value is 0.0808, which is definitely bigger than the value of alpha. So we do not reject. No. The only time we would reject is if that value goes below alpha.
So it always has to be bigger.
Yes. If it is bigger, if p-value is bigger than alpha, do not reject. No. Good. Good. Easier for you.
Oh,
So, so let's see. Can you see the calculator? Okay. Press start. Over to test. Now, this is where we did intervals, right? The t interval. If you have to pick something from options 1 to 7, based on everything that we did, which one would you pick? 2. T everywhere. So, t-test. You had the data. You entered the data in list 1. I don't have the data because I didn't enter it. I used Excel. So I'm going to go with the statistics that I wrote down. In the problem, we know mu naught. It is 98,000. The mean that you got was 92068.88. The standard deviation 0.61. The sample size is 16. This is the key part. You wrote the definition, you look at the alternative, and you can see as to why I kept stressing the fact that we always test for the alternative, because that's formal and standard. So of the 3 options that you see in that line, which one should you pick? First, second, third. Enter. Move on to calculate. Enter. The very first line that you see, negative 1.872, is the test statistic that we had earlier. The second line that you see, if you have to take a guess, what is that? It is the p-value. So you can get the test statistic and the p-value if the data is given, if the statistics are provided. But you should know how to interpret it. That's where the challenge is. Are we clear? We will do a right tail and two tail next week. Have a good day.